Welcome back. Hope you're doing well today. I have a very interesting problem for you, and it's definitely conceptual. This is for the civil and environmental FE exam. And I actually just created this for my civil FE exam students to help us learn concepts. Because nowadays, the real FE exam, civil, environmental, electrical, mechanical, and other disciplines will test concepts. It's not just calculation questions, plug and chug using the handbook. That's a very important skill, but at the same time, let's learn concepts, fundamental concepts, big picture stuff to prepare both for conceptual questions and plug and chug questions that use the FE handbook. If you're interested in getting a lot of hands-on practice where you will hit that magic number I always talk about, close to 1,000 practice problems under your belt, check out the link below specifically for the civil FE exam. And if you have questions, please let me know. Let's do this. We're told a river flows from left to right with the initial dissolved oxygen, DO, concentration upstream of all discharges. The river is assumed to be completely mixed vertically and laterally at each discharge point. Which of the following graphs, A, B, C, or D, most accurately represents the dissolved oxygen profile along the river from x 0 miles to x 100 miles, so for that 100 miles. So looking at this, we know we have a river, and that is clearly shown as this. It has a flow. That's the river. Now looking also, we have sources. So we have source 1 that discharges, source 2 that discharges, source 3 that discharges. These are the sources: discharge 1, discharge 2, discharge 3. Now the distance we'll look at here in this example, let's say 0, and we're going to take it up to 50, but after 50 we extend, and 100 miles will end somewhere all the way downstream. So 100 goes all the way to the end. That 100 is clearly shown in the graphs given. We have to select the right one for the dissolved oxygen. This is A. Notice y-axis is the dissolved oxygen, x-axis is the distance in miles. We go up to 100 for that 100 miles. How does the graph look like for the dissolved oxygen? Now looking at graph B, we have this. Continue with graph C, we have this one. And graph D, we have this one. You can pause the video and think about these. Graph D, C, then we have B, then we have A. Which one gives us the most accurate depiction of the dissolved oxygen that's going to be in the river itself? To help us with this, I want to relate this back to formulas in the FE handbook just a tiny bit. These will help us, and conceptually, it's all related back to this. If we want to specifically generate the right curve for the dissolved oxygen, and I'm going to actually attach a solution in the link below, so I'll talk about that at the end as well. So we know BOD exertion, this is how much BOD is used up by the microorganisms. No, this is how much they use. So this is relative to the ultimate BOD. Unfortunately, in the handbook, they don't provide a nice graph like they do for the PE exam. But just note, we start with the ultimate BOD, the L naught. Then that ultimate BOD gets used up. This is how much is used up by the microorganisms, BODT. Now this one's very important. This is actually the essence of the question and the concept here. Schroeder-Phelps gives us the dissolved oxygen curve that we will answer. So this D value is the deficit. This is not the dissolved oxygen. The dissolved oxygen is always what we start with, the saturated, minus the deficit. How much dissolved oxygen deficit we have. So this is the real value that we plot on these graphs that were given in this problem statement. Now, the few things here and the main parameters that I want you to focus on is the deoxygenation rate constant and deoxygenation. This implies decomposition. This is specifically, think of it as the oxygen used up by the bacteria. the oxygen used up by the microorganisms. So they consume oxygen and reduce the dissolved oxygen in the river. This is the rate. It's going to be that. Now there's a balance. There's going to be the reaeration rate constant. This is the one that adds oxygen to the river, that increases the dissolved oxygen from the atmosphere. In summary, KD is removing dissolved oxygen specifically by the bacteria that eats up the BOD, eats up the organic matter, that consumes dissolved oxygen, so it does reduce the dissolved oxygen, bacteria. Kr is reaeration. This is the oxygen added from the atmosphere. There's that balance between these, and we'll see how this is important. Now, going back to the question, let's look at this conceptually. So first of all, the flow comes in, and we know this flow will come in at a specific dissolved oxygen for that river, and it will have a specific BOD for that river. So we will say the BOD for the river, let's say it's a pristine, clean river, will be 0. BOD is organic matter. Think of it as the bad stuff, as we talked about in previous videos. So for a river, before the sources here, think of these as discharge industrial wastewater treatment plant sources. Before these sources, BOD in the river is close to 0, let's say pristine condition. It's very clean. It will have a high dissolved oxygen before, let's say, source 1. So that's important to know, and it will have a discharge for the river, Q for the river. Then it continues to flow, that river. Now we have the first source. Again, think of this as, let's say, from wastewater. That source comes in, and it will also have a certain flow rate, so Q for source 1. It will have a BOD for that source 1. That BOD, is it going to be 0 if it's, let's say, from waste, industrial? Definitely not. That BOD will get mixed up here, and it will increase the BOD at that location as soon as the river, the pristine river, which has 0 BOD, mixes with the source 1 discharge. So that has a BOD, let's say a BOD of 5, 6, 10, and then it will also have a dissolved oxygen concentration, which will be given, let's call it 1. So this is important to note that these two will mix together, and as soon as they mix together, we have BOD in the river. The formula is what? This was covered before in a different video. We can find that BOD at the source 1 here, where they mix, BOD of the mix equals, so let's plug this in simply. You take the Q for the river times the BOD for the river. Then you do the plus the Q1, Q for source 1, Q1 times the BOD for source 1. And then you take this divided by the value of what do we put at the bottom? It's going to be the summation of the flow rate. And you always do it this way. You always will do it this way. And this same concepts actually applies to the dissolved oxygen mix. All you do here is change the BOD to dissolved oxygen. So you can get the mixed dissolved oxygen as well using this crucial formula. Something to keep in mind, it doesn't have to be just 2 discharges, let's say a river and a source. It could be another source coming in this way. Could be a 4th source. So we just make adjustments to this very important formula. So we found the BOD at the mix, and that right there will begin to develop our curve. Right after this, we have the river with a mixed BOD. So that river continues flowing. Now the real question is, what will happen? So notice at A here, we start, this part is very important. This is the maximum dissolved oxygen. We call that the dissolved oxygen saturation. It does depend on the temperature of the river. We start with that. So we have at the beginning an initial deficit. In fact, all of these graphs have that. The deficit, initial deficit, which is going to be this. And that's actually our dA value in the formula, initial dissolved oxygen deficit in the mixing zone at the very beginning. So we have that deficit from the very maximum dissolved oxygen we can get for that river, which depends on the temperature of the river. We have that initial deficit. That deficit can be determined by taking dA will be dO sat and then minus the dissolved oxygen in the mix itself, which in this one, when we have that deficit, it will occur at source 1. So there is not just a BOD mix, there's a dissolved oxygen mix. Again, to calculate that, you just make adjustments to this formula, and you can find that as well. So we can get that initial deficit, and that's what's clearly shown. So this is an important concept. As soon as we have the source here mixing with the river, there's a deficit. There's that sharp jump down. So then we get to this point, let's say it's around 7. Now looking at the other graphs, okay, this has a deficit, good. Then we come back to 7. They're all consistent with that part, deficit. We come to 7 and we start here. Okay, this one, we have a deficit, then it starts at 7, then it jumps down again. So this one is different, but there's still that deficit at the beginning. Continuing on. So now we know this is the crucial part. There's going to be a curve developed. A curve developed where the dissolved oxygen on the y-axis goes down. Notice this one, it goes down in a way that's linear. That's never true. And look at the formulas. These formulas have an exponent. They have the natural log. That graphically does not look linear. So it's not a linear relationship. It is going to be a curve. So what I can do is eliminate this B. Let's take that out. So using our best estimation. So this one is still, I wouldn't say this one is linear. So let's say we can leave D in this case. So you can automatically eliminate B. It's not going to be linear. So we have the BOD in the mix. So that BOD will get used up by what? The microorganisms. Microorganisms, bacteria, use oxygen. They must survive. So they eat, think of BOD as the organic pollutant, the bad stuff, the trash. So the bacteria eats that BOD, then at the same time it needs to breathe. It uses the oxygen in the river. So what's going to happen is that oxygen will definitely go down after source 1. No, we're talking about after that location 0 here. The bacteria will eat that BOD that we have that got mixed up, BOD mix. So what will happen is a decrease, but it's not linear. It will be a decrease that looks like this. And this one, D, is absolutely out because we know here at 0 is where we have source 1, 0 distance in miles. At source 1, right after it, we know the dissolved oxygen will not go up. There's no way for it to go up because we have a BOD organic pollutant. When the river and source 1 mixes, that will, bacteria breaks down the BOD, uses up dissolved oxygen. Dissolved oxygen in the river does go down. So D is out. This dissolved oxygen goes up. So we're making great progress already. We only have 2 options, A or C. You might be already screaming and saying which one it is. Is it A or C? So let's continue. So this one looks the same as this one. So it does here, the bacteria is again eating up the BOD, consuming dissolved oxygen. So the dissolved oxygen does go down. So it does go down to a very important point that I want us to look at, and it's shared between both of these. This is the minimum dissolved oxygen. So let's write that here, DO minimum. And this occurs at a critical distance, which relates to a critical time. T for time, D for distance, C for critical. That's where the minimum dissolved oxygen will occur, at the very bottom. Both of these share it. So again, this one has the dissolved oxygen min. Just looking here from source 1 to source 2, from 0 to 25 miles, it will have a critical time, and it will have a critical distance where this occurs. That's where the dissolved oxygen min is located. And note this part here, that decrease is dominated by the bacteria using the eating up the BOD and also using the oxygen that's in the river. It's dominated specifically by the term. Which term would we say this? The case of the deoxygenation, that's the bacteria using oxygen to break down BOD decomposition. So this is dominated by KD up until the minimum. So dissolved oxygen goes down, down, down to the minimum. But notice something happens. It goes back up. So it does go back up around, let's say we're 25, let's say close to the 20 miles, 19, 18 miles. So somewhere here, that BOD will be less, and the river actually gets recharged. So it gets recharged after that minimum point. It recovers. Keyword recovery. That recovery occurs due to what? That will be the KR term. Reaeration of oxygen from the atmosphere. So in summary, we have a curve that goes down, hits the minimum dissolved oxygen. At minimum is going to be the critical time. Formulas in the handbook under Schroeder-Phelps. Critical distance, we can find the velocity will equal to the distance over time. If we have the velocity of the river, we can do calculations for the critical time if needed. Solution will be attached in the link below. So then we know that is going to be the initial part where dissolved oxygen, after that minimum, reaeration and recovery of the river dissolved oxygen, and then we hit source 2. So now here's the primary difference between A and C. Notice how this does the same thing. The dissolved oxygen goes down up to the minimum. Then we have the recovery, and then we have again mixing. So this would be another deficit DA2. This is deficit DA1. We repeat that same cycle. But notice each time this happens, the dissolved oxygen min actually increases. This does not make sense. So it does not make sense. It will decrease source after source if we have different sources adding BOD. What is correct is this. So this is our dissolved oxygen min that will occur somewhere here. The mix, BOD mix, we go get the dissolved oxygen min for this. Let's call it 1 due to the mix of source 1 and the river. So we know then we have another source that adds, let's even write this, a Q2, a BOD2, and a dissolved oxygen 2. That gets added. Now this part gets very, very tricky. We have the BOD mix here. That BOD mix does not stay constant. That BOD mix will actually decay and it will go down using this formula. So keep in mind the amount exerted will be this. The ultimate BOD that we have will be the L0. And that L0 is the BOD mix. Basically, the L0 we have, in this case, will equal to this. So we have to consider that we start with that value. That's the starting value, L0. We can find BOD t at a time, and we have the distance. Velocity of the river should be given. We'll see that in the solution below if you're interested in the calculations. So we get the mix again. We determine a new BOD mix here. BOD mix number 2, and we do have a dissolved oxygen mix that's number 2. Just do not say this BOD mix stays the same. It does decay. Let's say here it's 20, here it's 18, here it's 16, here will be, let's say, around 15 when it reaches source 2. So that BOD does change. It's accounted for by that formula. So we do the same thing again. So we start again here. We have a deficit dissolved oxygen, that deficit number 2. This is deficit number 1 where we have mixing. Then again, the dissolved oxygen will get used up by the bacteria, dominated by the KD term in the Streeter-Phelps. Then we hit the minimum, the critical minimum dissolved oxygen within that distance of the 25 miles, and rearrangement begins to dominate. We get recovery again. Then we go to source number 3. Now at source number 3, we still have the Q3 BOD 3 and the dissolved oxygen number 3 coming in. And again, that BOD of the mix that we determined here does not stay. Let's say it was close to 15, 14. It becomes 12, 13. Maybe here it becomes 10, that BOD. Then we calculate a new BOD mix at that location. Let's call it BOD mix number 3. It will also have a dissolved oxygen mix number 3. And we repeat the same cycle. But each time the dissolved oxygen min will go down. So we do have a deficit again. 3. The bacteria breaks down BOD. We have the KD dominated here by the decomposition. Then after the minimum point where we have the critical time and the critical distance, we have recovery due to reaeration from the atmosphere. It should be A for this one. That is the most accurate depiction for this river. Now, I do have a PDF for you breaking all the calculations down. This is definitely good for the environmental because it will use this definition and it will use the Streeter-Phelps. So what we're doing essentially is going one source, so small distances at a time. We will focus, break this down first into this, into that distance, which relates to a certain change in time. Then after taking care of that, what happens at the end of source 2 is still considered, but then we move on to that part of time. Then we finish off for the final distance from source 3 to the 100 miles. Full calculations will be attached below. Definitely will help you. It's very involved, but this is designed again to test concepts. Hope you found this helpful and keep up the good work.